Hi guys, how's it going? Today actually we're gonna be talking about how we can actually design a chat application. So you can think of today's content as a more like system design uh, type of a content. So by chat application, I'm referring to applications such as WhatsApp, Facebook Messenger, those type of systems. So you can think of it essentially as a software messenger which provide text-based instant messages services between the users. So with that said, what are the requirements for building such a system? Like what are the key features that we're gonna have to discuss? Obviously we're gonna need a private chat. By private chat, I mean like the user has to talk to somebody else, right? Like you support one-on-one conversation going on. So we have to have something like that. So in contrary to the private chat, we need to have a group chat, right? So you can think of like we have members who invite one another, then they talk on that group chat. Like so, because of that, I think it will also be good to add the leave and join feature, so the users should be able to join and leave the group as they wish. Then we should be able to also add that we need to keep track of online users, right? So when the user is online, offline, we need a mechanism to check that for status purposes. When it's more like a last seen type of a feature. What's next? So we can look at what happens when the user is offline. So we need to send some sort of like a notification. That notification essentially is going to hit the device itself. Like the device could be Samsung, Hawaii, you know, uh, because the user is offline. Okay. So discussing now the non-functional functional requirement, I want to talk about the most important thing. I think like it's the minimum latency, and the reason I'm prioritizing minimum latency is because I want the users to have a real-time chat experience, right? Real-time chat experience. It's like when you send a message now, you want that message to get like instantly, right? So minimum latency should be prioritized, and consistency can take a hit. So I'm gonna go with high availability. So here the reason I'm choosing high availability, it's okay for the message to take 2 seconds delay. So when also I'll think we are not building like some sort of like a transactional application like ordering system whereby consistency is quite important, like so hence like I'm going with high availability instead of consistency. So yeah, in adding to that, I think also the system should be highly scalable. Okay, so with that said, let's move to the capacity estimation. So, with capacity estimation, you can think of like we try to estimate the load that the application is gonna take. So this essentially help us to make good decisions in terms of the designing our system overall. So we can assume that we we have like 500 DAU daily active users. So let's say 5 million. I mean to say DAU. So DAU simple refers to daily active users. And on average, we can say that each message, right, has some sort of like 100 is around 100 characters on average. a message has 100 characters. Okay, so each person, also this is an assumption that each person send about 80 messages a day. Okay, so a day. So based on this, right, based on this above, we can say the database will be horizontally scalable because we'll be having some sort of like 150 gig a day. So storing 150, the messages that we're going to store is going to amount to 150 gig a day. So we should make sure that the database is horizontally scalable due to 150 gigabyte of messages per day. Okay, we're definitely gonna need a globally distributed system. Okay, distributed system. Like WhatsApp is an application whereby writes are greater than reads. So meaning that people write more than they read messages, right? So there's many messages coming through, like also given that each person writes like 80 messages a day. So there's more writes than reads. And this is also important to keep in mind because when we go to the next step, we'll see how it actually influences us to choose what databases we should go with. Okay, so yeah, just keep that in mind for now. So the next step that we're gonna discuss is like some sort of like APIs, right? High level design of the APIs. Just gonna. So how are we going to like how are we going to design the API? So the first API, we can say it's the get all group, right? So we want to get all the groups that the user has joined. So we can think of like we provide a user ID, then we get all their groups that they have joined. We can also have an API for leave group. So this is more like given a group ID and the user ID, the user can leave. We can make that user to be excluded from that group. Then the second one is also going to be join group, which is also similar. It's going to have the same parameters as group ID and user ID. And we can have a mechanism, an API also to send messages. So we can have a user ID, okay, and we can have the receiver ID, and we can have the channel type. So by channel type, I'm referring to whether this is a private or a group channel. And yeah, we can have a message here. Okay, so definitely we can have many parameters, but I just want to keep it as simple as that. So we can have a get message. So with this, we can also take the user ID 1 and user ID 2. Then we can also take the channel type to know where are we getting those messages from. and we can have an earliest message. So ID. So this actually enables us to make sure that the user gets messages in according to the order that they have been sent. Obviously, we need some sort of like in this API. I did not mention this, but maybe we can have some sort of like a key that authenticate the user to send all of these messages, right? So that's something that you should be aware of. Okay, so let's get to the database design. I'm just gonna choose a white pen this time. So let's talk about how we're gonna design. Before we get into the schema, I wanna like support all the decision and why we're choosing this whatever we're going to choose. So we definitely know that writes are greater than reads for this application that we're talking about. So we have more writes, more people are writing messages than they read messages. So we need some sort of like an optimized database for writes, which is right. So a huge number of small messages that need to be inserted, right? So we can have an LSM tree, and so there's databases that have this, and there's databases that are B tree, and doing this essentially helped me to be able to classify all the database that we might need. And B tree databases are read or lookup optimized, right? Whereas with LSM tree, we have update and write optimized, right? So we know that we want to go with like the LSM tree, so we don't want this. And so given that, we can then go with a column oriented database. So this is more like a NoSQL databases. So for example, it could be Cassandra. Another reason is that, guys, we're not like designing an e-commerce system whereby like an SQL, in contrary to this, SQL database are more like relationship heavy, right? Like you need to like have relationships. In our case, I don't think we are the system that we're designing, it's relationship heavy compared to within e-commerce you have like orders, you have like products, like there's more relationship. So hence a NoSQL database is chosen in this case. Okay, so yeah, one of the best practices with modeling data with Cassandra is that you need to understand. Firstly, you need to understand the access pattern. So, how is the data going to be queried first before you start modeling? So I thought it would be a good idea to start with that. So, let's start with all the write operations that we're going to have to do. So we definitely know that we need to add delete user from a group. So we're gonna have to delete add a user from a group. Okay. We're gonna need to commit messages in a group. Okay. We're gonna need to commit messages in a group. We can also gonna have to commit messages between user A and B. Also, I think the read portion of things is quite important. So because that's how like we're gonna get the data from the DB. So let's say if you're given like 2 users, we need to retrieve their messages. Like you still remember the private chat, right? So we have to say that if we're given two users, given user A and B, get their messages. Just for your information, the reason we're doing this is because these are like access pattern, and the reason we're doing this is because how we're going to model data in Cassandra, because we don't have relationship. So you can think of like we need to partition. They're calling it partition. We need to store this data in like its own table. So hence, it's quite important for us to know how we're going to access the data. But when we get there, I'll actually expand on that. So secondly, we need to say if because of users will be in the same group, so we can say group chat. So we need to say that if we are given a specific group, we need to return the message. So given a group, right, retrieve all the message up to certain point. All the message. Okay. Also, we can say given a group, like retrieve the member's ID. So this one, the reason I'm talking about this is because it's more like when you want to broadcast all the messages, right? So let's say a user send a message, send that message to all the other users in the group. So hence, we need to, given a group, we need to retrieve all the members' ID. Similarly, we have to say given a user, find all the groups, find all the groups that the user has joined. So with that said, we're gonna go into the schema now portion. So with Cassandra, we have two concepts called partitioning and sort. Some call it clustering or clustering key. So just write it down. So we have the partition key, and we definitely have a sort or clustering key. Okay, so essentially a partition allows us to let's say like we partition by a specific column. So essentially it's gonna make sure that all that data is stored in the node, and the sort is gonna make sure that that data in a partition is sorted by the sort key. So that's what it means essentially. So with that said, we're gonna start with the direct message. So how does the table looks like for direct message? By direct message, I'm referring to the private chat, right? So we can have a user A and we can have a user B. So this is more like a sender, and the receiver, we can have a timestamp of the message, and we can have the message ID. Okay, and we can definitely have the message here. So something like hello. So because like you still remember our access pattern says that given user A and B get the message. So which means that we definitely want to partition by this, right? Because this is gonna make our life easier. So it's like you can think of like we have nodes, right? We have nodes, right? Servers, something like this. So this user's data will be in one node. So it will be much faster to retrieve their data if we partition it by these two columns. So imagine if like you're partitioning by, let's say, one column, then you're going to get the user data here. Then you still need to go to another node to search for that data for user B. It was going to be clunky and the latency was going to increase. So this will definitely be our partition key. Okay, then we want to retrieve, as we're retrieving this message, we want them to be somewhat sorted, right? So we can sort by the message ID, assuming that the message ID is an incremental ID in a way. The incremental ID is quite involved. By that I mean like there's more optimization that they do. Like I think Twitter uses Snowflake ID. It's a key generation service that they have. So that's what I mean by involved. So it requires quite a lot of work and optimization to make sure that, because of we are working with distributed systems, so to make sure that we have a consistent IDs across. Okay. So now modeling our group chat table. So we can have a group ID. Okay. We can have the message ID, and we can have the timestamp. We can have the message and the user ID. So we can partition this table by the group ID, but we can actually run into a problem of having a huge number of partitions. So in this in Cassandra, having a huge number of partitions, it can actually drastically affect your performance. So I'm going to introduce a new column called bucket, and we're going to use these two tables, these two columns to partition as our partition key. And the message ID is going to become our sort key. So it is also important to know that essentially the message ID is used here to determine the ordering, right, of the messages, so that we can retrieve the latest messages in the group. But it's also important that in the Cassandra deck, the distributed database like Cassandra, the scope is usually determined by the partition key. So it's not ideal to rely on this only. So you're gonna need a separate service like what Twitter has. Twitter has like Twitter Snowflake ID, like a generation service that, or like service like that is going to help you to make sure that the IDs that are being generated are consistent across as you write to the table. That's one thing that you should keep in mind. Yeah, with that, now let's look at modeling the group table. So this is like the group membership table. So we can think of like we have a group ID and we have a user ID. Then we can keep the partition key and we can sort. We can keep the user ID as a sort key, and we can also have a user membership table. So these tables, essentially we having them because they help us to broadcast our message. For instance, if we want to every time a user has to send a message to in a group, we need a group ID. Then the group ID is going to give us all the users in that group. Then we send the message to all of them. So that's why we need these two tables, and we partition by the group ID. Gonna be partition key, and this is gonna be our sort key. Okay. So also the user membership table is for listing all the groups a user has joined, so we can be able to see all the users that the user has joined. So we can look into also having a user profile table. Okay, so with the user profile, we can have a user ID, can have a password, salt hashed password. It's going to be hashed, and you can have a status that shows whether they're online or not, and you can have a profile image stored on some sort of like S3. Maybe this could be a link of the photo, and yeah, and yeah, this is like the user ID. So essentially this table is gonna help us also to get the user status because we said we want that feature. So hence I had to talk about that also. So now let's get into the high architecture design and see how the whole architecture is gonna look like. Let's talk about the high level architecture of the system that we're trying to build, right? So so you can think of like high level architecture. We showing how all of these components will work as a whole, and we're gonna discuss them in more detail. So we can think of like we have users, right? You wanna call them client, that's fine. So we know that these users somehow they have a private chat, right? So they have to exchange messages between one another. But we need to do this in real time. And we need to use a protocol that can actually exchange this message in a more like a peer-to-peer communication, so that we can have that real time, like we spoke about that real time requirement, right? So which means that we need some sort of like a WebSocket. We need to use a WebSocket, which has a TCP protocol, and it has the peer-to-peer communication. So it's going to essentially enable us to send messages, enable the users to send messages and receive these messages. Okay, so as messages are sent, these messages we need a service that is going to be able to manage this outgoing, incoming messages, and make sure that it persists these messages in sort of like a database, right? So which means that we need a new service here. We can call it a chat service. So it's just going to make sure that it receives the messages and it sends the messages, and it has this WebSocket server. So theirs is going to detect new messages as message comes, and it's going to send them just like that, right? So it enables that real-time requirements that we spoke about. So we can say, okay, when messages comes, we want to persist the messages, so we can actually have a database here. Okay, and that's that. Another requirement that we needed was to say users can leave groups, users can join groups. So we can treat that in a separate route. For instance, let's say we have a service here called web service. So this is for the user wanna join, leave, login. Okay, so we don't need to have a WebSocket protocol, the gRPC protocol. We can have a HTTP is fine for these services. So we're gonna treat them in a separate route. Okay, so because these are client initiated. Okay, so client is the one that gets to say, okay, I need this and I need to leave or something like that. So it's fine. We can treat them on HTTP. So that's that. So another service that we spoke about was that we want some sort of like a notification. So let's say we said that we send the message here, right? We said that we send the message, but if the message here, because on the WebSocket we're gonna try to send the message in real time to the receiver, right? But let's say the receiver is offline, so we need some sort of like to say, okay, when the user is offline, how about we then call a new service, which is we're gonna call a notification. Okay, so this is gonna be notification service. So you can think of here we have also the servers. Okay, to avoid overwhelming this system, we can have a queue here. We can queue all of this, right? So this system, essentially the notification system, when the users are offline, it's gonna push this to the user's mobile device. So we can have it like go to the client device. So let's do it like this. So go back to the user, send the message on their mobile device to alarm them that they have a new message that they need to accept. Okay, so another requirement that we had, guys, was that we need to check if the user is online or offline, right? So we can have a present service here, right? Which we're gonna talk about in more detail also, and how it's gonna work. So it's gonna read, and also it's gonna read from this service and write from the present to see if the user is online. So that's another service. So all of these things, we're gonna discuss them in more detail as we go on. This is a HTTP server. So another important component is the mapping of the servers, right? So we're gonna need a mechanism to map the servers. Actually, let me just remove this high level architecture. So each WebSocket, it's gonna need to send messages on a specific WebSocket server. So we need a way to know which messages have to be handled by a specific server. So we're gonna need a user mapping service. I'm gonna discuss everything in more detail, guys, so don't worry if you don't understand. This is just the high level architecture. So this is a mapping server, and yeah, distributed just like so. So yeah, that's the high level. So essentially, the user mapping service, it enables us to keep track of the server ID of the user session. So yeah, when the user sending each other messages, so they use a specific server ID. So we need to get that. So we need a service to handle that portion. So now we're gonna look at in more detail. We're gonna look at the first thing that we're gonna look is the data flow. So how does the data flow, right? So we can say, given the user, let's say user A, right? They can send a message because our system is globally distributed. So each region has a WebSocket server. So we can think of this WebSocket as like WebSocket number 101, and every time the user send a message, we write the message before we acknowledge them. So we're just gonna write the persist the message first into the DB, which is number 2. Then we acknowledge that. Okay. But then where's the message going? Where is the message going to? Before we send the message to the receiver, the WebSocket will then first get the WebSocket server for the receiver. So let's say the receiver is user B, right? Then it's gonna call that service that I was telling you guys about, which is the mapping service. So this is the mapping service. So it enables us that given the user, get us the WebSocket. So this WebSocket is 102. So now we send the message to that 102 server. So this is step number 5. Okay, we say message goes to this WebSocket, which is where called WebSocket 102. Then we push the message because like that's how WebSocket works, right? Pushes the message to the user, and this is user B. Okay. Now, looking at the notification service, I'm just gonna copy this. Copy. So now let's discuss the failed send message, right? So let's say we somehow we can't push this, right? So the user here is not available. So we can't find this user here, right? So what we need to do, we need to then queue that. We're gonna push it to the queue. Okay, we queue it into this. This is you can think of this as the queue. Then we have a notification service. Right? A notification service essentially is gonna allow us to get a user B phone number. So let's say 062 that and that, and then it's gonna push the message to Hawaii Samsung phone, and it's gonna try to send them a notification that they have one new message. Okay, so that's that. So just walking you through the high level architecture, it's this portion here. Okay. However, there's a possibility that when the user actually reconnect, there's a possibility that that user might not actually receive those messages, right? So how can we handle that? So upon the reconnection of the user, that was offline, we need them to still retrieve all the previously sent messages. So we're gonna call this a history cache up. Okay, so how this will work is that given user, we can have an API that says get history. So for user A and B, after a certain timestamp, okay, they can hit a HTTP. This is user initiated, so we don't have to use a WebSocket. We're using the HTTP server. Okay, so we're gonna read all the messages that were sent while they were offline, and those messages will then, we're gonna call them undelivered messages, will go to the user. Okay, so from a table perspective, we can think of like we have this, and we have a user ID 1, user ID 2, we have the message ID, and we have a timestamp, we have the message, right? So these message probably were sent, then these ones here, we will say, are you there? Was not sent because the user was offline. So we need to retrieve them. Okay. Regarding the group chat, how do we handle group chats, right? How do we send messages, for instance, like to all the users? For instance, what I'm saying here is that let's say we have user A, we have user A, and they send the message to WebSocket 101, and we know that when they send the message, the WebSocket will then write the message to the database. Okay, which is right. This is step 2. Then also we need to get from the database, get member, get group members. So if you still remember from our design, was that given, like from the schema design, was that we had a group ID, right? And we had user ID. So we know that given a group ID for G412, we can get all the users here, something like that. So in this case, let's say the WebSocket managed to retrieve user A or user B and user C, right? Then it calls the mapping service to get all their WebSocket. And the WebSocket that associated with users is the 102 and 103. Okay, obviously we'll have acknowledged after from the writing to the database. And now we forward all of these messages to the respective users through their connected WebSocket. So we're gonna say WebSocket 102 will push the message to the user B. So this is user B, and we forward the message to WebSocket 103, and we push it to user C. So essentially this is how we broadcast all the messages in the group to all the users. Coming to the present service, one way we can go about present service detection. By present detection, I mean like the service that check if a user is online or not, right? So one way we can go about it is that we can open a WebSocket that detect the heartbeat of all the users. Like each user send a heartbeat, then we broadcast that to all the user's friend. Then the friend can see that the user is online, right? But that way of doing it is gonna be way too expensive. It can actually overwhelm our system. So how can we do it? And we know that like some people have like 1,000 friends on WhatsApp, but they don't necessarily like talk to all of them. So it does not make sense to check all the user status, something like that. So we need some sort of like a smart algorithm to detect the most frequent chat for that specific user, right? So we can say, given a user, we can have a user A, and this service user A sends some sort of like a heartbeat, right? And this goes to the WebSocket. Okay, WebSocket 101. This WebSocket, it goes under the present service. Okay, present service, which is gonna get the user. So it's gonna say get user A, and the present service is gonna give the user A all the frequently contacted people, right? So maybe let's say we want like top 10 of your, the close people that you always talk to, it's gonna get them. Then maybe let's say this is user B and C. When you get this, you now they need to like see their status in real time, right? So what we need to do is that we need to get their WebSocket. So it's going to be user mappings. We're going to get their servers is 102 and 103. Okay, then we just push that status. So you can see on the device there for a specific David, you will see that it says online, something like that, right? So that's what it will say. But now this is only top 10. What about their other friends? What about the rest of the people? Those users can actually use a pool mechanism. So they can use a pooling on presence. By pooling we mean that they can directly like go and refresh and get their status for a specific user themselves. So with the top 10, we push the status to them. We show them that okay, who's online. But for these other users, they can actually pull the status. So getting into more details into our system, we have made decisions such as communication between the servers, right? So like, are the servers supposed to communicate in a point-to-point manner, or is there supposed to be a middleware between them, right? So I think this is quite important for us to cover as part of the detailing the system. So it's like communication between web sockets, right? So it could be easier to separate and have a synchronous HTTP call for each message. So what I'm saying is that we can have a WebSocket 101 and it can hit 102 WebSocket. A point-to-point communication, essentially, it might not work mainly because problems such as network bandwidth. So let's say the user send messages in a sequence, like maybe something like "Hi" or "How are you." It is possible for this first message to be delayed due to network bandwidth, and there's so many things that could make this one happen. So what this lead to is that there will be no message ordering, and we know that message ordering in a chat-based system is very important, right? So keeping the order of the message is quite important. And the second thing is that a point-to-point communication, given that we have like a lot of users, so large request per second, um, is gonna overwhelm the servers, right? So the servers will be overwhelmed by the number of requests that will be sent between these systems. Okay, so this might also become a bottleneck. Okay, so maybe you might be thinking, okay, cool. Then how about then we use a middleware, right? We have these WebSocket 101. We can have some sort of like a queue, right? Kafka that then send the message to WebSocket 3, and we can distribute all of these queues like so, and we can send all of this to 103 WebSocket 104, right? That's one way we can go about it. However, given the scale of like Facebook Messenger, WhatsApp, um, maintaining and scaling WebSockets, queue I meant to say, sorry, um, it's very expensive, and to scale them can be also be difficult, right? So another thing is that this architecture comes with things such as, what if the server goes down? Because what if the consumer, like, right? What if the consumer goes down? Servers come and go all the time, right? But what if it comes down? Like, how do we uh because of the user will have to be reconnected to a new server, right? And their messages, this server is connected to this queue. How will they then do a history cache up to get all the messages that were sent to them while the server was down? How will they do something like this, right? Like, how do we handle like stale messages in the queue? Do we discard them? Do we process them? All of these challenges, right, comes um, into like the complexity of the system overall. So to avoid that, we can come up with a synchronous HTTP solution that could get us halfway through the problem. So what happened is that we can store each message with some sort of like a sequence number. So we can think like we have, let's say we have a user, right? We have a user A, and we have a user B. Okay, so when the user send a message, for instance here, if they say the message is hi, we essentially need to keep the previous message ID and the message ID. So let's say the previous message is equals to 1 and the message ID is equals to 123. Okay, so if it happens that for some reason we send a message because of, like I said, network bandwidth, this message here, so the user sent this message, but it takes time to get to user A. Instead, this one gets first, right? And this one, it was like saying, "How are you?" So this is me. This is just an example. How are you? And the previous message here, it was 123, and the message ID is 125. So here we're gonna detect. We're gonna say, we can see, we're gonna see here that okay, the previous message is 123, but then this is 125. We'll see the anomaly that this does not make sense. So what we need to do in that case is that we need to then um, call an API that we designed, which is called get history. So we can get the history of the messages, like to get the previous message. So provided user A, B, earliest message equals to 123 and 123 and get all the messages. So that's that. So yeah, the point that I'm making, guys, is that if we have a sequence, we sequence these number, we have a sequence number. This is actually going to help us to know that we have 123, we have 125. It doesn't make sense. So we needed to get 124, something like that. So essentially, this is like the solution. So now the question might be, how do we then implement the buffering portion, right? So to reduce the number of message exchange between servers, right, we can definitely implement a buffering algorithm uh, on WebSocket server, right? Just to make sure that we don't overwhelm the system. So we can do that, and this solution, it's easy to maintain compared to the queue system. So, and it solved the problem of ordering because of we have a sequence number of each message, and the problem of buffering is going to be solved with the algorithm that we can build. I think also a Go language has this mechanism, can do that. Another optimization that we can think of is how do we handle how do we handle sending messages in a group chat, right? Sending messages in a group chat. So the reason I'm raising this is because you can think of like the current system that we have. If a group has like 100, I don't know what's the limit. Like let's just make a very very large assumption. Let's say each a group has 100K users, right? So when each user send a message, right, that message then will have to be sent to all the 100K 100,000 users. So this will be an expensive write operation, right? And it could actually slow down the system. So we need a way to solve this. And before we get into that, I want to say that there's two ways this is actually done, which is that it's called pushing and it's called pulling, right? So with pooling, the user hit all the HTTP request, right, to request all the messages that have been sent in the group, right? And with pushing, we with WebSocket we push all the messages to the users, right? So the users get the messages. Um, so with pooling, the problem here it could be that uh, each user, like 100K, like all of them, they're gonna have to pull the message, right? So each message is read multiple time. I think this is called read amplification, right? So it's gonna have that. Then with pushing, uh, we end up like writing those messages to all the users. So also it's gonna be quite expensive. Okay. So is there a way we can optimize this? We still want the users to get the message. I think it's a nice feeling for the user to get the request that they have a message. We wouldn't want them to all the time refresh to see if they have a message, right? So I think we can find some sort of like a way we can do this, which is that we can write an algorithm that asks if the group size, right? If the group size is small, like group size large and no, then it's fine. We can push, right? Because it's small. So maybe it's like 10 users in a group, right? It's fine. We don't mind pushing all the messages as they come through to all the 10 users. That's okay. And the second one is that okay, the group is large, but we wanna all know if the group is active, right? So there are certain groups that are not active, right? So if the group um, is quite active, right, then we can have a pull mechanism, right? And if it's not, we can push the messages. So the reason here we pull is because the group is active. Everyone is always gonna try to is already talking in the group, so they always gonna refresh and try to see all the new messages. But the problem with the one which is not active is that we want to keep the users who are not active in the group to know that they have a new message, something like that. But that is just the high level algorithm that we can have. Okay, so with that in mind, guys, that's like the system design. So there's certain things that I did not discuss. Like there's so many things um, um, that we could have discussed. Need improvements. So I think we didn't talk about catch. Like something like catch. We didn't talk about I think we should have most talk about fault tolerance, also and replication, right? It's an area that we can look into. I think also we could have probably spoke about load balancing, right? So I'm just talking about all the things that I think would have we could have spoken about, or maybe improved in a little bit. Yeah, I think that's that, guys. Thank you for tuning in, and I really appreciate it. I'll see you guys in the next one.